In late 1960s, string theory was firstly studied broadly. In that span of time, it was studied under the name of nuclear force. Later on, the field of nuclear force was left by this theory, as this theory started being applied on various concepts of quantum chromodynamics. Therefore, the fact became known that string theory is not familiar to be applied on nuclear physics theory, which made it a thing of concern for quantum theory of gravity. Bosonic string theory was the earliest version of modern string theory. In that version, only the class of particles were included and described. These class were known as bosons. The subsequent version to bosonic string theory was superstring theory. Superstring theory described connections between symmetry and bosons, class of particles. This connection was referred as fermions. In the time span of mid-1990s, there were more than 5 versions of superstring theory were developed. However, they limited the scope that is possessed by a whole theory by dividing the theory into various, almost 11 dimensions. This concept is known as M-theory. Connection between string theory and quantum field theory was developed in late 1997. This connection, or let us say relation, is well known as correspondence of ADS or CFT. Fifth dimension in gravity theory was introduced in 1914. This introduction was carried on by Gunnar Nordstrom, in which he described both electromagnetism and gravity too. In this approach, he tried to describe the concept of electromagnetism with his very own theory of gravity. This is the first ever modification attempted on string theory. Later on, Einstein superseded this approach by introducing non-symmetric matrix tensor. In addition, later, actually much later, Brans and Dake pursued this approach and introduced their research by developing the concept of scalar component of gravity. These consequences are said to be major approaches in the field of string theory. The original concept of string theory was produced in the time span between 1960 and 1970. In that, theorists did not consider time the string theory, as it was not able to provide complete help for the problems surrounding to hadrons, protons and neutrons, all are subatomic particles, etc. Despite of these early researchers, development or say history of string theory is divided between 2 phases. The first one is known as first superstring theory. Time span of this revolution was between 1980 and 1994. In beginning of this period, it was discovered that neutrino, a chiral fermino, could not be accommodated by any quantum gravity theory. Edward Witten played an important role in this research. As consequence, he collaborated with Louis Alvarez Gaume and pursued his studies further in the field of conversation laws, which is a part of anomalies gravity theory. Later on, a new anomaly was discovered, which these both missed. As a result to this foundation, scope of a string theory group, gauge group, was restricted to be SO. As a result to this, Witten was convinced that string theory is a fully complete edition of theory of quantum gravity. He made his identity as a high-profile advocate as a result thanks to his researches. Hundreds of physicists and mathematicians pursued their study, taking Witten's researches as a base. This all happened in the time span of 1984 and 1986. This time period is known as First Superstring Revolution in the field of string theory. In 1995, birth was given to new 11-dimensional theory that we know now as M-theory. The time period in which M-theory was being developed is known as Second Superstring Revolution. Fundamentals of string theory. Almost all fundamental interaction in which gravity is also included are a part of string theory. Thus, almost all theorists and physicists believe that string theory is a theory of everything and is able to describe anything that is a part of our universe. Currently, research on string theory is being conducted in order to find a valid solution to the many problems related to microelementary particles that has small cosmological constants. These constants contain dark matter and a cosmic inflation mechanism. Progress has been made in order to achieve these goals. Hence, it is not clear if the string theory is really a universal theory or not. As described above, string theory has not yet managed to give a complete definition for a certain thing that can be applied in any situation or circumstances. This is said to be a big fallback for string theory. Until now, string theory is being applied using a perturbative approach. It is not yet discovered how to apply this theory non-perturbatively. To understand these statements, it is important to understand fundamentals of string theory. Strings. In quantum field theory, practical application of mechanics to physical objects is presented in an extended form. In that theory, these concepts are extended to space and time. Various physical events are calculated in the field of quantum theory using perturbation theory techniques. To organize various calculations, perturbation theory uses Feynman diagram. These diagrams are considered as paths of point-like particles. These paths also indicate interaction of particles along with particles themselves. Bosonic theory is said to be the most basic version of string theory. The problem with that version was that it described only bosons. Bosons are particles classes that transmit force between various matter particles. They are known as fermions. This version is replaced by superstring theory. This theory includes both bosons and fermions too. This theory incorporated use of supersymmetry. Supersymmetry is a mathematical relation between bosons and fermions. This relation can be found in various physical theories. Except supersymmetry, there are various other versions of string theory. Type 1, Type 2a, Type 2b are some of them, each with its own new concepts and theoretical approaches. Type 1 includes both open and closed strings, where types 2a and 2b describe closed strings only. Extra dimensions. Generally, there are 3 dimensions in the field of space, with which we are familiar. These 3 dimensions are height, weight, and length. However, Einstein treated time as a dimension in his general theory of relativity. In that theory, Einstein formed a 4-dimensional space-time by merging time and space. To do so, he did not treat time and space as individuals. It is certain that space-time, which is a 4-dimensional unit, describes universe in a well-organized structure. Still, other dimensions are considered by many physicists in order to achieve new methods in order to extend approaches in this particular field. It should be noticed that to maintain consistency in mathematical operations in string theory, one need to add an extra dimension that is extracted from 4-dimensional space-time. In bosonic version, space-time has 26 dimensions. The number reduces to 10 in superstring theory. There have been many approaches made in order to reduce the number of extra dimensions in space-time. Physicists who made these approaches tend strongly believes that observable universe holds only 4-dimensional structures and possesses a high-dimensional space. This concept is important when one is trying to develop real-time physics by using string theory as a base. Dualities. Almost every version of string theory follows non-trivial was in their approach. This kind of relationship between various versions of string theory is called S-duality. According to this relationship, a set of particles that strongly interact with each other according to one theory may have a very weak interaction according to a completely different theory. Another relationship between various string theories is T-duality, which says that each string theory circulates around an extra dimension. Duality is a situation in which 2 different systems that possess different physical concepts are proven similar in a non-trivial way. Here, it should be noticed that duality relationship can be only applied on concepts of string theory or string theory itself, as it does not provide consistency in other fields. Duality relationship means that if 2 theories are in duality relationship, one of them can be transformed with some changes. However, the operations in 2 different theories cannot be made similar as they have different bases. Duality describes that 2 different theories possess some phenomena, yet have differences in mathematical operations. As an example of S-duality in the field of quantum theories, Montanen and Olive duality can be considered, in which ADS to CFT possesses the duality that builds a connection between quantum theory field and string theory. Brands. In the field of string theory and related concepts, brands is known as a physical object. This object is used to increase the level of dimension of a point particle by generalizing its notion. For instance, dimension level is 0 for particles and it is at level 1 for strings. This is just an example. However, brands can possess much higher dimension too. Brands is considering as dynamic objects that follow the rules and regulations of quantum mechanics in order to operate through space-time. They also possess attributes such as charge and mass. Brands are also studied in the fields of pure mathematics. In setting theory, D-brands are considered important class as they descriptively include open strings in their concepts. As string theory drives its concepts through space-time, it requires use D-brands as a base of the process. M-theory. In the beginning period of 1995, many theorists had believed that there are 5 versions in total of this broad theory, which are as following: Type 1, Type 2a, Type 2b, Heterotic string theory 1, Heterotic string theory 2. This statement was proven wrong when concept of M-theory was presented. In 1995, Edward Witten suggested that these 5 theories written above are just limiting versions of main 11-dimensional M-theory. This announcement leads a huge influence of a physics field. Many physicists rushed for further research using M-theory as a base that multiple researchers are now known as second superstring revolution. Unification of various superstring theories. Supergravity theories describe a combination of general relativity with supersymmetry. As a result, in 1970s, many theorists and physicists became interested in this particular theory. By the arrival of 1978, it has been discovered that if 11 is taken as maximum number of dimensions, it allows formulations of consistent supersymmetry. In the same period, it has been proved that supergravity cannot permit any more dimensions than 11. 11 have been proven as a maximum number of dimensions allowed by supergravity. Thanks to these researchers, many physicists started to believe that by using the concept of supergravity with 11 dimensions, it would be possible to build real-time models of 4-dimensional world. They also hoped that these models would help us descriptively study fundamental elements of 4-dimensional world. These elements are listed below: electromagnetism, strong nuclear forces, weak nuclear forces, gravity. Chirality, which is a phenomenon, caused a problem in practical application of 11-dimensional concept. The problem was that basic laws of physics were being distinguishing between clockwise and anti-clockwise phenomenon. Later it was accepted that 11-dimensional concept is not yet developed completely to solve or cover this problem. During the time period of first superstring revolution, many theorists and physicists had accepted string theory as a combination of particle physics theory and quantum gravity theory. Supergravity theory was not able to solve the chirality problem. Unlike that theory, string theory not only solved the chirality problem, but also provided an updated version of gravity theory, which also included the concept of quantum effects. However, in the time span of late 1990s, many physicists were arguing if there are less than 5 supersymmetric versions of this theory. It is proven that string theory has only less than 5 consistent versions. A combined version from these multiple theories is yet to be developed. However, as the research was pushed further, physicists started a close examination and deep studies of a string theory. They eventually stumbled upon the fact that these multiple versions of string theory are related with each other. Some of them were related through intricate way and some were related in non-trivial way. Eventually, it had been also discovered that there are not much difference between strongly interacting strings and weakly interacting strings, except the level of interaction. The fact, or say phenomenon, is known as S-duality, as described in a subtopic above. After 2 or 3 years, T-duality relationship was also discovered. According to this relationship, two equivalent strings can belong to completely different space-time and different geometries. At the same time, handful physicists were trying to apply string theory on high-dimensional objects and try to describe properties of string theory. In early 1987, two-dimensional bands were discovered as a part of 11-dimensional space. Look of these objects was very similar to sheets. These sheets, like objects, were found to be propagating through 11-dimensional space-time. Later on, a new concept was developed in which one of the dimensions was considered as a curled-up circle. According to this concept, it can be imagined that the bands are wrapped around that circular dimension. Now consider that the radius of that circle or dimension is small enough so that on a 10-dimension level the bands can be viewed as a whole string. The pattern of these objects were much similar to string that appear in second A version of superstring theory. Matrix theory. According to the definition provided by mathematicians, matrix is an array of numbers or other kind of data that is sorted in a rectangular order of specific size. The definition of matrix in physics is much different from one given by mathematics. According to physics, a particular theory which involves the notion of matrix in its mathematical formulation is said to be a matrix. A matrix model refers to interaction between a set of matrices that are a part of quantum mechanics framework. In 1997, through the BFSS matrix, an important example of matrix model was presented by a small group of researchers. A set of 9 large-size matrices was represented in that approach. They proved that 11-dimensional supergravity is responsible for the low energy limit of any matrix model. These results are enough to prove their BFSS model much similar to M-theory. As a result, in many researchers, BFSS matrix model was used as a prototype model of original M-theory. The purpose of using that model was to find exact formulation for M-theory. Many physicists also use this model deeply to describe M-theory properties. These researches were helpful in the process of linking matrix models with M-theory. They also constructed a relationship between matrix modes and geometry that has a non-commutative nature. By using these results as a base, many physicists managed to discover important relationships between non-commutative geometry and multiple physical theories. Concept of black holes. Generally, particular area of region of space-time that possesses a super-strong gravitational field is known as black hole. Their gravitational field is too strong for any particle or radiation to escape. As according current researchers and most accepted models, black holes are formed when a massive or even a small star enters its state of gravitational collapse. It is said that there are supermassive black holes present in the center of each galaxy that exists in the universe. Black holes hold a specific theoretical importance since, in many researches, theorists are using them as a base to learn quantum aspects that are related to gravity. String theory holds a framework of thermodynamics which is important for one who is studying properties of black holes based on their thermodynamics only. Bekenstein-Hawking formula. Statistical mechanics is a well-known branch of physics. Entropy is a measure described in statistical mechanics. This measure is mainly used for randomness or say disorder of any physical system. It has been studied in late 1870s. In that very same period, it was discovered by an Australian researcher, Ludwig Boltzmann, that combined properties of multiple molecules of gas can help to derive thermodynamic properties of gas. Not only had this, But he also proved that by tuning behavior of gas molecules, one could derive following microscopic properties of gas: temperature, volume, and pressure. Through his researches, he proved that entropy is a natural algorithm which is used to derive different states of the molecules that are known as microstates. These results led many theorists to discover macroscopic features of various physical objects. By the beginning of 20th century, the very same concept was applied to black holes by many researchers and physicists. They used gases and entropy scales for such application. In 1970s, it has been proved that entropy is related with the surface of event horizon of any black hole. This concept was represented by Jacob Bekenstein. Event horizon of a black hole is the boundary where matter, particles or radiation is lost due to the super strong gravitational attraction of black hole. By combining the result of his researches with the results of Stephen Hawking, Bekenstein presented a formula to find mathematical value of entropy S. S equals C3Ka to 4Hg. Values presented in the formula above are as following: C equals speed of light, K equals Boltzmann's constant, H equals reduced value of Planck constant, G equals Newton's constant, A equals surface area of even horizon of related black hole. Every black hole has relative entropy like any other physical object or system. It is related to different microstates. These microstates offer very same macroscopic features as described above. This formula is capable enough to find expected value of any black hole. However, in 1990s, physicists attempted to account microstate in the theory of quantum gravity. As a result, they lacked a derivation for the very same formula. Thus, it is considered important to find such a derivation, which is similarly important for the viability of any quantum theory, say especially for string theory. Concept of phenomenology. String theory is a collection of multiple frameworks with different purpose. Some of its models are also used to construct real-world physics models. These models are used to construct a combination of particle physics and general relativity. Phenomenology is one of the many branches of theoretical physics. This branch describes how one can build real-time models with abstract theoretical ideas. In the field of string theory, it is known as string phenomenology. In this concept, it describes how real-time or semi-real-time models can be constructed by using only string theory as a base. There is no practical evidence to prove these models practically correct. There are two reasons for such failure. First, theoretical and mathematical difficulties, and second, to test these facts practically, a high amount of extreme high energies are required. Due to this approach has been criticized by many communities or individual experts. Some also doubt on the unification of questions and values derived through this approach. Particle physics. Standard models of particle physics is the most accepted theory in current time. This theory contains descriptive information about particles and their interactions. In this very same theory, three fundamental forces of nature are covered and studied, which are as following: strong nuclear forces, weak nuclear forces, electromagnetism. However, this model has failed to provide complete description of real-time objects. Despite of its descriptive information and resources, main reason behind its failure was that it failed to perform a complete incorporation of the force of gravity. There were also minor problems such as hierarchy problems. This model could describe neither fermions mass structure nor dark matter completely. Crossing the limits of standard models, models of particle physics can be also built using concepts described deeply in string theory. Compactification is used as a base for construction such models. Physicists managed to postulate a shape for extra dimension by starting with 10 or 11-dimensional space-time. By applying or using this shape in proper method, similar models to the standard model can be constructed. These models also include undiscovered practicals. If one wants to derive real-time physics from string theory, one needs to start applying heteroic theory by assuming 10-dimensional space-time. It should also be assumed that there is extra space for almost 6 extra dimensions. These techniques offer multiple approaches and methods that help a lot to derive real-time physics from string theory. Real or semi-real model for 4-dimensional universe can be also constructed with the same method with minor changes. Thus, this technique can be also applied in M-theory. Cosmology. The Big Bang theory is said to be the earliest known cosmological model. It covers a subsequent and large scale of evolutions. In this successful and well-structured theory, following features of universe are observed and explained: galactic redshifts, hydrogen and helium as a relative abundance of light elements, proving the reality behind cosmic microwave. However, Big Bang theory could not answer many questions, and they are unanswered until the date. Some questions whose answers are not found in Big Bang models are as follows: why universe tends to be equivalent in each direction? On very large distance scales, while universe becomes flat? What is the reason for not using magnetic monopoles and other hypothesized particles in practical implementation or experiment? An alternative theory to Big Bang concept was developed by multiple experts in 1980s, which is known as theory of cosmic inflation. The cosmic theory includes and accepts all the concepts of Big Bang theory being true, but it also includes explanation for some unanswered features of the universe. According to this theory, cosmic microwave radiation was spread around 380,000 years after the events of Big Bang theory. This incident was responsible to fill the sky, says inflation theory. Criticism upon approaches of string theory. Number of solutions. It is important to specify a certain shape for extra dimension in space-time in order to construct real-time physics models that are completely based on string theory. Each individual shape is related to a possible universe. Collection of particles and forces vary from unit to unit for such shape. There are around 10,500 nose vacuum states or possible universes according to string theory. They are enough to derive any phenomena that are observed through two different energies. Many critics are concerned about the large number of possible universes in string theory. Critics argue that because of large variety of universes, string theory is almost useless to predict anything. If someone picks up certain option among them, his result would be only related to that universe. However, some experts also see this number as a virtue. As a reason, they say that a large number of available universes allow the examiner to observe values of physical constant closely and extract natural observation through it, and that too about cosmological constant that holds a particular small value. Many string theorists accept these facts, but they do not claim string theory to be completely wrong. Some of them see this as a virtue and some as an error or say bug. None of them supports critics claiming the theory completely wrong. Background independence is one of the fundamental properties of general theory of relativity, which was presented by Einstein. Background independence means that two formulations contained in a particular theory with this independence cannot refer to particular space-time geometry. Some critics argued that string theory fails to maintain such independence. According to string theory, a fixed reference to geometry or space-time needs to be specified. Thus, any other geometrical calculations are described as reference to this fixed one. Critics argue that string theory badly fails to maintain this important general activity for each turn described in string theory. These facts rejected by some string theorists. One of these string theorists, Polchinski, pointed out that quantum gravity theory has a major problem in developing holographic description for gravity, which is why it does not require gravitational field to be anti-de Sitter. Moreover, this is the exact reason why string theory does not possess background independence. As a response to Polchinski, Smolin said that the facts presented by Polchinski are unproven future results, rather than being facts. He noticed that the whole concept of general relativity and quantum gravity is based on global symmetries because geometry of space-time is completely dynamical. Sadly, this debate is still going on, and the truth is still to be found. Many critics are trying to understand string theory even better to find and explain bugs in it, and vice versa. Some theorists are studying it to fill the holes. Sociological issues. String theory has been considering a valuable and useful resource for the studies of high-energy theoretical physics since the first and second superstring revolutions, those who took place between 1980s and 1990s. Many string theorists believe that there is not any similar theory that can answer fundamental questions of physics as string theory does. They strongly believe that there are no viable alternative for string theory are available. Many critics have responded negatively to these kinds of statements from multiple string theorists. Despite of the popularity of string theory among physicists, Peter Voigt considers string theory as an unhealthy and detrimental for the future of pure physics. He thinks that financial structure of academia and fierce competition to scarce resources are main reason behind the popularity of string theory. Many critics use this thought to build up their own opinion about string theory. Statements stated by Voigt are widely accepted. Even some string theorists accepted them as a fallback. A critic, Penrose, believes that many young researchers prefer using pre-made bases to establish a new research, rather than building new resources on their own. He claims this statement as a reason for which string theory is very popular among physicists and researchers. Lee Smolin says that the rise of string theory discourages foundation of physics, despite the theory being all about physics. He prefers to follow loop quantum gravity theory, which, according to him, encourages the fundamentals of physics and radical thinking. Until the date, any critic or string theorists have not managed to prove themselves completely right. In simple words, no critic has proved string theory completely wrong, and no theorist has proved string theory completely right. The debate is endless until now. However, some experts have hope that one day it will end and they will have a conclusion to the topic. Some accept the loopholes in the theory and strongly believe that this debate is never going to meet an end. As described through various chapters and concepts, string theory describes almost all fundamental concepts of modern and pure physics. Yes, there are many loopholes in this broad theory, for which solutions are still to be found. Some string theorists believe that one day, by constant researches, the theory would be turned out to be complete. On the other hand, some of them have accepted string theory as it is. It is same with the critics. Some are trying to prove it completely wrong from the base, and some have accepted it in incomplete form and believe that there are no more unknown errors left in it. As a researcher, student, or practitioner, one must accept the theory as an incomplete one. This way, he can fulfill his purpose of practicing string theory. Ignoring all the criticism will help the practitioner a lot to accept the concepts and facts presented in the theory. If criticism is concerned, then no concept in the theory is left complete. Critics have covered almost every concept present in the theory, thus it is strongly recommended to learn the theory as a complete theory, with certain errors, or say, exceptions. With electromagnetism and gravity too. In this approach, he tried to describe the concept of electromagnetism with his very own theory of gravity. This is the first ever modification attempted on string theory. Later on, Einstein superseded this approach by introducing non-symmetric matrix sensor. In addition, later, actually much later, Brands and Dake pursue this approach and introduce their research by developing the concept of scalar component of gravity. These consequences are said to be major approaches in the field of string theory. The original concept of string theory was produced in the time span between 1960 and 1970. In that, theorists did not consider time the string theory, as it was not able to provide complete help for the problems surrounding two hadrons, protons and neutrons, all are subatomic particles, etc. Despite of these early researchers, development or say history of string theory is divided between two phases. The first one is known as first superstring theory. Time span of this revolution was between 1980 and 1994. In beginning of this period, it was discovered that neutrino, a chiral fermino, could not be accommodated by any quantum gravity theory. Edward Witten played an important role in this research. As consequence, he collaborated with Louis Alvarez Gaume and pursued his studies further in the field of conversation laws, which is a part of anomalies gravity theory. Later on, a new anomaly was discovered, which these both missed. As a result to this foundation, scope of a string theory group gave In late 1960s, string theory was firstly studied broadly. In that span of time, it was studied under the name of nuclear force. Later on, the field of nuclear force was left by this theory, as this theory started being applied on various concepts of quantum chromodynamics. Therefore, the fact became known that string theory is not familiar to be applied on nuclear physics theory, which made it a thing of concern for quantum theory of gravity. Bosonic string theory was the earliest version of modern string theory. In that version, only the class of particles were included and described. These classes were known as bosons. The subsequent version to bosonic string theory was superstring theory. Superstring theory described connections between symmetry and bosons, class of particles. This connection was referred as fermions. In the time span of mid-1990s, there were more than 5 versions of superstring theory were developed. However, they limited the scope that is possessed by a whole theory by dividing the theory into various, almost 11 dimensions. This concept is known as M-theory. Connection between string theory and quantum field theory was developed in late 1997. This connection, or let us say relation, is well known as correspondence of ADS or CFT. Fifth dimension in gravity theory was introduced in 1914. This introduction was carried on by Gunnar Nordstrom, in which he described both each group was restricted to be SO. As a result to this, Witten was convinced that string theory is a fully complete edition of theory of quantum gravity. He made his identity as a high-profile advocate as a result thanks to his researches. Hundreds of physicists and mathematicians pursued their study, taking Witten's researches as a base. This all happened in the time span of 1984 and 1986. This time period is known as First Superstring Revolution in the field of string theory. In 1995, birth was given to new 11-dimensional theory that we know now as M-theory. The time period in which M-theory was being developed is known as Second Superstring Revolution. Fundamentals of string